presented in the form of graphs. Normally, an RTOW chart for each type of contaminant is used by operators. The table is used in the same manner as those for dry-wet runways. When taxiing on slippery surfaces, maintain a low forward speed. Use nose wheel steering for directional control, supported by differential thrust as necessary for small radius turns. Anti-skid is not operative below 15 knots. There is little risk of ingestion of contaminant during the takeoff, except during crosswind conditions when small amounts may be ingested by the inboard engines. Such small amounts of ingestion will not degrade engine performance, but continuous ignition should be on for the duration of the takeoff. After takeoff, if climb-out performance is not limiting, delay retraction of the landing gear in order to shake off any accumulated slush. Takeoff should not be attempted when more than 15 millimeters, 0.59 inches, of surface water or the water equivalent depth of slush or loose snow covers more than 25% of the runway surface area within the required length and width being used. To have a water equivalent depth of 15 millimeters, the depth of other contaminants are 18 millimeters slush, 38 millimeters wet snow, or 75 millimeters dry snow. Following limitations for takeoff from contaminated runways are valid. Flap 30 and maximum takeoff thrust must be used. Cabin engine air bleeds must not be used, and air brakes, lift spoilers, all-wheel brakes, and anti-skid systems must be fully serviceable. Performance is based on standard tires and pressures. The assumptions for takeoff on dry and wet runways are applicable to takeoff on a contaminated runway, except that flap 30 is always used. VGO is a speed for engine out continued takeoff to a screen height of 15 feet. No credit for clearway is taken, and allowance in the calculation is made for landing gear displacement and spray impingement drag. According to valid certification and operation rules, V1 must be equal to or greater than VGO and equal or less than V-stop. When V-stop is greater than VGO, either value may be chosen as V1. The AFM recommends that for standing water, slush, and loose snow, the higher value V-stop is chosen as V1. This will minimize the engine-out acceleration period to unstick with high contaminant drag. For compacted snow and wet ice, it is recommended the lower value VGO is chosen. There is no contaminant drag retarding acceleration, and therefore stopping from the lowest V1 possible on the lower friction surface should be given priority. This consideration should be included in the performance chart output. Last but not least, the following reduced crosswind limitations should apply during takeoffs from contaminated runways, depending on braking action, respective friction coefficients. Aircraft approved for flap 33 takeoff have additional limitations. Takeoff is not permitted on contaminated runways. N1 ref must not be less than 87%. Reduced or flexible thrust is not permitted. Engine air must not be used for cabin air conditioning during takeoff, and 12 degrees must be added to the ambient temperature before entering the RTOW chart when engine anti-ice is used. The AFM permits the aircraft to be ferried in specified abnormal configurations for the purpose of reaching an airfield where repairs can be carried out. Ferry flights may only be undertaken if the AFM for the aircraft includes the appropriate appendix covering the specific configuration. Limitations apply in each case, and the handling techniques are covered in the appropriate FCOM Volume 3, Part 1, Chapter 8, Ferry Flights. The choice of cruising level varies with the route, aircraft weight, ambient conditions, and the sector distance to be flown. In normal operations, the cruising level will be given on the computer flight plan. Detailed climb performance is presented in tables with the instructions for their use in FCOM Volume 2. These tables give information about fuel, distance, and time regarding brake release weight against cruising level for long-range and high-speed climb. When using the tables, note that operational performance assumes cabin air bleed is selected to recirculate, anti-ice systems off, and climb thrust assumes the use of the climb max setting. Time, fuel, and distance in climb are all increased when the anti-ice bleeds are used. There is a corresponding reduction in cruise distance and fuel, and the net effect on sector fuel and time of climbing through a icing layer 10,000 feet deep is given in this table. Regulations require that in the event of an engine failure en route, the aircraft must always be capable of ensuring at least the minimum net vertical clearance of terrain or obstacles for continuation of the flight to the planned destination airfield or return to the airfield of departure or diversion to any suitable en route airfield. A positive climb gradient 1,500 feet above the airfield of intended landing must be achieved. Regulations further require the aircraft to be able to comply with the following requirements. The gradient of the net flight path must be positive at least 1,000 feet above all terrain and obstructions along the route within 5 nautical miles for EASA, JAA, or 5 statute miles for FAA on either side of the intended track. The net flight path must permit the aircraft to continue flight from the cruising altitude to an airfield where landing can be made. The net flight path must clear terrain and obstacles by at least 2,000 feet along the track within the above specified lateral limits as long as the net flight path is negative. In the event of engine failure during cruise, ensure the optimum flight path by following the procedure. Maintain the current cruising altitude set, and maintain maximum continuous thrust, MCT, if the IAS decreases. Allow it to reduce to VER in level flight, VER plus 20 knots above 27,000 feet. Maintain VER or VER plus 20 knots by commencing a drift down until the altitude stabilizes. As weight decreases, adjust and maintain the appropriate VER. The aircraft will continue to drift down until it reaches an altitude determined by its weight and the ambient conditions. This is the stabilized net ceiling. The aircraft may stabilize above this altitude as safety factors are included into performance. The stabilized net ceiling assumes a clean aircraft with cabin bleeds on and fresh selected. There are separate tables in the FCOM for engine and airframe anti-ice either on or off. If the aircraft is operated along a route which is more than 90 minutes at long-range cruise away from an airport suitable for diversion, a 2 engines inoperative drift down has to be considered. The procedure is the same. The net flight path has to clear all obstacles 2,000 feet vertical and has to be positive 1,500 feet above the airfield of intended landing. Tables are provided in the FCOM for air condition on and full bleed load. The net flight path is for certification requirements. The gross flight path reflects the actual aircraft performance. There are also gross drift down tables within the FCOM for the explained cases. The net flight path data must represent the actual performance diminished by a gradient of 1.6% for a single engine failure and by 0.5% for a double engine failure. Time, fuel, and distance for descent in ISA conditions to a given arrival weight is presented in two tables. For high-speed and long-range descent, the tables are almost the same as already discussed in the climb section. Time, fuel, and distance in descent are all increased when the anti-ice bleeds are used. There is a corresponding increase in descent distance and fuel, and the net effect on sector fuel and time of descending through an icing layer 10,000 feet deep is given in this table. The allowable landing weight is the lower of the weights determined by the landing field length limit, the approach climb, or the landing climb limit. In addition to the AFM, there are two sources of landing data information for use on a day-to-day basis: the Flight Deck Handbook, FDH, and regulated performance charts. The landing weight field length limit assumes landing flap 33 or, if permitted, flap 24. Flight idle selected at 50 feet and ground idle selected after touchdown. Air brakes open or closed in flight and open on the ground. Lift spoilers deployed after touchdown, and full wheel braking with operative anti-skid system. FCOM data assume a wind component not more than 50% of reported headwind component and not less than 150% of reported tailwind. These factors have been taken into account, so the actual wind component can be used without factoring. Altitude refers to airfield altitude, and wet runway field length required is 115% of dry field length. As you see on this AFM chart, the approach climb gradient of 2.7% required for four-engined aircraft is usually not limiting, only at weights above maximum landing weight and at very high pressure altitudes. For a flap 33 landing, the go-around flap setting is 24, and for a flap 24 landing, it is 18. Of course, approach climb capability is better with flap 18. Be careful when evaluating your approach and landing data. The approach climb gradient of 2.7% is an air value which does not account for any wind component, but the missed approach climb gradient assures obstacle clearance and therefore depends on wind. If the missed approach climb gradient is above standard, which is 2.5%, adequate engine out climb capability has to be assured as dictated by regulations. This AFM chart deals with the landing climb gradient. A value of 3.2% is required by the regulations. Also, the landing climb is only limiting at very high altitudes and weights. The FDH contains landing distance required tables for a range of weights for the following: dry, wet, and contamination with compacted snow, dry or wet snow, slush, standing water, or wet ice. Tables for each condition above give the landing distance required for weight, pressure altitude, and head or tailwind component.